Welcome to Electronic Devices and Circuits Lab. In this video, we are going to obtain the input and output characteristics of transistor in common collector configuration. So let's begin the video. So first of all, we have to make a circuit. That circuit you can look at in this particular picture. Okay. This particular circuit we have to implement onto breadboard. So in this lecture, I will be using the MultiSim software to obtain the input and output VI characteristics in common collector configuration. So first of all, we need to implement this circuit onto the MultiSim. So here you can see that we have to use one NPN transistor. And here I will be using this particular model BC547BP. Okay. So any of the NPN transistor you can use. Okay. And here you can see this particular terminal. This is our emitter terminal. And this will be our base terminal. And here we have our collector terminal. So here you can see in the common collector configuration, this collector terminal is common to both input loop as well as in the output loop. So here you can see in this input loop, we have to connect one resistance of 100 kilo ohms. And here in the output loop, we have not connected any resistances. But however, you can connect any small resistance in the circuit if needed. So in this configuration here, you can see while obtaining the input characteristics, what we have to do is we have to first vary this particular potential. Okay. So here you can see that we are applying a certain supply at this particular point, which is regarded as VBB. Okay, in my MultiSim model, I will be regarded this particular voltage as Vin. Okay, so here you can see this is VBB supply, and you please note down this particular polarity of this particular battery. Okay, here you can see that this negative terminal of the battery is actually connected to this resistance. Okay, this is connected to this particular base through this particular resistance. Okay, and here we have to connect one multimeter to measure the current, okay, through this particular circuit. And here again, we have to connect another multimeter to measure this particular current, okay. And then here you can see this potential, okay, this potential is referred as VEC, okay, it is emitter to collector potential, right? This is our emitter terminal and this is our collector terminal. So this is our emitter to collector potential. Again, you note down this particular polarity, okay. Here this terminal is negative and this terminal is our positive, okay. So now what we have to do, we have to implement this circuit and then we have to try to obtain the input characteristics as well as the output collector characteristics. Fine. So if you see in many of the books, you will see this particular characteristics. Okay, this typical characteristics of your common collector configuration. So it will look like something this. Okay, you can see this particular characteristics. Okay, so this is our input characteristics in which onto this x-axis here you can see we have to change the collector to base voltage. So here you can see this will be the potential. We are actually talking about collector to base voltage, or you can write base to collector voltage. Okay. So first we have to change the this particular potential, and because of changing this particular potential, obviously this base to collector potential will also change. Okay. And then we have to measure the variation in the collector, this particular base current. Okay. So there will be a certain base current flowing through this particular terminal. So this base current we have to measure by changing this particular input voltage. And then we have to note down this potential, base to collector potential, and we have to measure this particular base current. Obviously, this two parameter will be measured at the fixed value of emitter to collector voltage. So this emitter to collector voltage we have to fix. So that you can see from this graph itself. So here you can see this graph. Okay. In this graph, you can see this is our graph. Okay, so here you can see that in this particular curve, okay, here we have the collector to base voltage, and then onto this y-axis we are having the base current. Okay, and this base current will be having its magnitude in microamperes order, and this curve is actually obtained for VCE equals to 5 volt. So you remember that here we are writing VEC, emitter to collector voltage. And here we are writing collector to emitter voltage. Okay, it is collector to emitter voltage. So whenever you are giving VEC, it will be a negative voltage because of this polarity of the battery. But when you write VCE, it will become positive quantity, right? So this curve has been obtained for VC equals to 5 volt, VC equals to 10 volt, VC equals to 15 volt, and so on. So this way we have to obtain the family of curves by varying this particular VBB. And because of the variation in the VBB, there will be change in the corresponding change in the base to collector voltage will be observed. So that we have written as base to collector to base voltage. Okay, so don't bother about it. If you write base to collector voltage, it will take negative signs. Okay, here it is 4.35, 10, 15, whatever it is. So this will be taking a negative sign. Okay, if you write base to collector voltage. Similarly, to obtain the output characteristics of this common collector configuration, what we have to do, you again see we have to actually vary this particular potential. Okay, we have to vary this particular emitter to collector potential, and then we have to measure what will be the current. Okay, what will be the emitter current, and what will be the potential across this two terminal. Okay, because we have not connected any resistance, whatever be the emitter collector voltage you are applying, the same voltage will appear across this emitter collector terminal. So we have to plot a graph between emitter to collector voltage and current. Okay, this two graph we have to obtain for a fixed value of base current. This base current should be a constant. Okay, so here you can see this curve also. So how we have obtained, here we have written as collector to emitter voltage. So that's why this potential will become positive. Here you can see we are writing collector to emitter voltage, and here we have applied emitter to collector voltage. Okay, so because this is negative terminal, so when you're writing collector to emitter voltage, it will become positive. Okay, here you can see this is connected to positive. So here you can see it is varying from 5, 10, 15 volt and so on. And then we are actually here measuring the emitter current. Okay, here you can see this emitter current. Okay, the order of the emitter current will be in the milliamps that you can measure. Okay, so that current you will be measuring through this particular multimeter. Fine. Then you can see this curve, this family of curves are actually obtained for different values of base current. So here it is IB equals to 0. This base current will be 0. We have to set this base current by controlling this input voltage. Okay. Then again, IB equals to 10 microamps, IB equals to 20 microamps, and IB equals to 30 microamps. So this way, we have to obtain this two curve. Okay, these two input characteristics and output characteristics in the common collector configuration. So here I have written several steps, few steps. You can note down these steps. Okay, if it is required, I will be explaining you onto the MultiSim. Okay, so this way you have to perform. You can just follow this all steps. Okay, just you go through it, you read it out, and then you can. Then you have to make this observation table, right? So this observation table you have to make for common emitter voltage equals to 2 volt. You have to measure this VCB and IB. Similarly, for VC equal to 3 volt or 4 volt, then you have to measure this VCB and IB. We have to tabulate all these results. Okay. Similarly, for output characteristics for IB equals to 0 microampere, we have to measure this two quantity, collector to emitter voltage and emitter current. And this is again collector to emitter and voltage and emitter current for IB equals to 20 microamperes. And so this way we have to perform our experiment. So let's go to this MultiSim software. Okay. So this is our circuit, whatever I have shown there, the same circuit I have implemented onto this MultiSim. So here you can see that this is our NPN transistor. Okay. And this is my emitter terminal, right? This is your arrow sign. So here it is emitter terminal. This is our base terminal, and this is our collector terminal. So this collector terminal is actually common to both input loops and output loops, and hence it is regarded as common collector configuration. Fine. So here you can see that this in this input loop we have connected 100 kilo ohm resistance, and then here I have connected one multimeter to measure the base current. Fine. Here I am calling this particular potential as V in. Okay, and then we have to change this V in, and then accordingly we have to set the IB currents. Okay. Here you can see in this output loop, we are having this emitter to collector voltage. Okay, this potential, this is the negative potential which is connected to this particular emitter terminal, and this positive is connected to this ground. So this way we have to first make the circuit. For simplicity, what I have done is I have connected some multimeters. Here you can see we have to, because in the input characteristics, we have to measure this base to collector potential. Okay, to measure this base to collector potential, I have connected one multimeter over here. You can see this. Okay, this is our multimeter. So this multimeter reading is coming over here. Okay, this is multimeter number 4. So this multimeter reading is coming over here, right? Similarly, here you can measure the emitter to collector drop. Okay, so although it is not needed if you see this circuit, okay, because there are no resistances connected in the path. So whatever emitter to collector voltage you will be applying, the same emitter to collector voltage will appear across these two terminal, emitter and collector. So this particular voltage, this particular multimeter is not required. But if you connect any resistances, that time this particular multimeter will be needed, okay, to measure what will be the emitter to collector drop. So that can be measured by having a multimeter. Again, this is where base terminal and this is where emitter terminal, right? So this base terminal and emitter terminal, again, I have connected one multimeter to measure the potential across these two terminal, right? So here you can open it, you can measure the voltage, fine. So now here you can see that to obtain the VI characteristics, okay, first of all, you have to understand how this circuit works, right? So basically here you can see, because it is an NPN transistor, okay, this terminal is N type, this is P type material, and this is again N type material. So here you can see that this makes a PN junction, fine, this makes a PN junction, base emitter terminal. So whenever this base emitter terminal will be forward biased, this transistor will be in the conducting state, that you have to remember. And you must be aware that for the silicon transistors, this base to emitter voltage drop should be around 0.6 to 0.7 volts. Okay, if it is a silicon transistor, because it is corresponding to its cut-in voltage, fine. So whenever this base to emitter terminal voltage is around 0.6 to 0.7 volt, then this transistor will get turned on and it will be conducting heavily. And that time you will observe certain base currents, okay, of significant magnitude. And similarly, you will be going to get certain emitter current into this particular output loop, fine. So now here you can see in this configuration, right, because the way we are applying the polarity, it is very important to know when this particular base emitter terminal is getting forward bias. So once it will be getting forward bias, then only you will be getting certain base current. Otherwise, if it is not getting forward bias because of the applied potentials, then it will be in the turn off mode, and you won't be able to observe any current, any significant base current or collector current. So that we have to remember, right? So how to ensure that whether it is base to emitter terminal is forward bias or not? So what we can do is we can write a KVL expression, okay, a Kirchhoff voltage law. You must be aware about the Kirchhoff voltage law, that you can write around the device, okay, around this transistor. So if you write a KVL expression around this transistor, what will be the expression that you can see? Let us suppose that this voltage drop, base to emitter drop, is regarded as positive. This terminal is positive and this is negative. The way I have connected this multimeter here you can see this potential is positive. I'm considering this terminal to be positive and this to be negative. Okay. Then again, I'm considering this terminal to be positive, this to be negative. And then again, it is this particular potential. This is, I'm considering negative and this is positive. Okay. So if you take this signs into consideration, and if you write the KVL expression around the transistor, you can write this as VBC minus VBE plus VEC equals to 0. Okay. Please verify this, okay, how to write this KVL expression. So here you can write a KVL expression around this loop, fine. So you can write this KVL expression around this loop, and because this is negative, this is positive, it will be considered as positive. Negative to positive is positive, and then positive to negative, it will be negative. Okay, VB is negative, then again, negative to positive, it will be positive. Okay, so overall, base to emitter voltage that we are going to get is VEC plus VBC. This is the base to emitter voltage. So that we have to remember, fine. This will be in the base to emitter voltage. So you can verify it while observing, while doing the experiment, right? So now we have to start our experiment by obtaining the input characteristics first. Okay, so how to obtain the input characteristics? As I already explained in the input characteristics, first of all, we have to fix the emitter to collector voltage. Okay, for a particular voltage of emitter to collector voltage, we have to change this V input. Okay, so once we'll change the V input, due to change in the V input, there will be corresponding change in the base current. Okay, and there will be a corresponding change in the base to collector drop. Okay, this drop will also change, fine. So we have to observe these two quantities. We have to change this V in, we have to observe what will be the base current through this multimeter, and this multimeter reading is coming over here. Okay, So this reading we have to note down, and then again we have to also note down what is the potential drop across base to collector terminal. So here you can see this observation table. I have already made it. Okay. So for common collector input characteristics, first of all, we have to opt in the for V is equals to -2 volt. Okay. For V is equals to minus, first of all, you please make this observation table. Okay. So this is V in potential. Okay. This is V in supply. Okay, obviously, I have not put it there negative sign, but obviously this V in with this polarity only, right? Whatever the polarity I have shown here, this should be negative side of your potential battery, and this is the positive side. Okay, so this negative side will be connected to this particular base terminal. Okay, and then this potential we have to vary. So once you will choose this V in equals to 0 volt. Okay, you have to make it 0 volt, and then you have to apply this V is equals to 2 volt. Okay, -2 volt. So here you can say this circuit. Okay, I have already applied V is equals to 2 volt because this terminal is connected here is negative. Okay, so just mind this polarity. Okay, so V is equals to 2 volt. Fine. So now if you make it 0 volt, here you can make this value equals to 0 volt. So once you will make it 0 volt, then you can execute this circuit. Here you can measure this current 13.238 microamperes. This is 13.238 microamperes current. You can note down here. It is okay, 13.238 microamperes. Okay, it is in the microamperes range. And what about base to collector drop that we have opted is -1.324. That you can verify from this. Okay, this is our multimeter. This is the reading of this particular multimeter. Okay, -1.324. So this way we have opted our first reading. This first reading. Okay, this reading we have opted. Fine. Now for the second reading, again, you can just make it V equals to 0.5. So if you make it 0.5, first we have to stop it. And then again, just make it 0.5. So if you make it 0.5, again, you can make this observation. You remember that we have to keep this VEC constant. Okay. It will be kept constant up to means at 2 volt. Fine. Again, here you can see after making 0.5, here you can see what is the base current, 13.238. Okay. You note down this value. This is 13 point. IB equals to how much it is. Okay, we have not executed the circuit. First execute it. Okay, so after executing it, we are getting this current equals to 8.374 microamperes. Okay, so here you can observe this is 8.374 microamperes. And what about the base to collector drop? It is -1.337. So you please observe this value, -1.337. Okay, so this way we have obtained the second combination. In a similar fashion, you can check out any other combinations. Okay, so just you try to check out this value. Okay, -1.4. This particular value -1.4. So when we'll be making this V in equals to -1.4. Okay, what will be the reading? So before that, what one more observation that you can observe here is when we made 0.5. Here you can see this base to emitter drop. It is around 0.6 volt, 0.662 volt, and therefore we are getting a significant current. Okay, when it was 0 volt, here you can again see when you made it 0. Again, you can see this base to emitter voltage drop is, you can see it is around 0.676. So it is near about 0.7. So already this transistor is in turn on condition. It is already in the on condition, and therefore we are getting a significant amount of. Once you will start increasing this voltage, you have already observed this current is decreasing. Okay, so now if you substitute this value, okay, I'm just trying out this particular value, -1.4. Okay, so try to make it -1.4. So I'm just making -1.4. One important point here is that because it is MultiSim, it is a software, I can make it -1.4. Okay, I'm not changing the polarity over here, but while doing the experiment onto the breadboard, you have to remember you have to change the polarity. Okay, you have to change the polarity, then you have to apply 1.4 volt. Okay, you cannot make like this. Okay, cannot put any negative sign onto your breadboards. So whenever you are performing any experiment in your laboratory, you can't do in this way. You remember. Okay, this is onto the MultiSim only. I am putting this negative sign. Fine. So now it is -1.4. So if you execute this one, you will find that this current is 27.018 microamperes. Okay. So here you can see this current value, -1.4. If you make it -1.4, sorry, this is not minus 1.4, it is plus 1.4 only. Okay, I have written wrongly over here. Actually, this all value should be negative. Okay, remember that, because already V in is already negative. Okay, because all these values are negative, because V in is already negative. So you just make it 1.4. Okay, not negative. Please remember that. Make it correct. Okay, so it should be 1.4. We are increasing the value right from 0 volt, and all these values are actually negative. Okay, why it is negative? Because here you can see this polarity. Okay, this negative side of the battery is connected to base. Okay, so it should be negative. When you writing over here, it should be negative values, right? These all values are negative. You can write minus 0.5, minus 1 volt, minus 1.2. That way you have to substitute all these values. So now if you execute this circuit again, you can see this voltage drop, base to emitter voltage drop, you can observe it is falling down. Okay, it is 0.56 millivolts. Okay, 0.56 volts. Fine. So here you can see this current is also dropping. So now this current has become 0.33 microamperes. Okay, so that current I have already noted down there. Okay, 0.33 microamperes. And then you can see this base to collector drop is minus 1.433. So this value is minus 1.433. So this way you can try this all other results. Okay, I have already conducted this experiment. So you can see this table and you just try to verify all this data. Okay, you remember these potentials are all should be shown in negative. Okay, and you can obtain all this complete table. So what table I have obtained? I have gone up to this minus 2 volt, and then I have obtained this results. Okay, similarly you can change this V in. Okay, here you can change minus 2, minus 2.5, minus 3, minus 3.2. Okay, so here I have stopped at minus 2. The current has dropped to 0. Then again I have changed the VEC value minus 4 volt. So I'm just showing this result. Okay, so if I make it 2 volt, okay, if you make it 2 volt, I'm just stopping it, and then I will be making it 2 volt. So once you will make it 2 volt, and if you execute the circuit, okay, once you will execute this circuit, you can see this current is almost in the nanoamperes, very small current. Okay, very, very small current. Okay, in comparison to your microampere. So this current is very small. So it is negligibly small. Okay, so I can make it 0. And here you can see this potential drop. Okay, across base to collector terminal is minus. This base to emitter voltage is very small, very, very small, and no current is actually passing through this circuit because it is in the turn off conditions. Okay, it is in the already off mode. Okay, so that observation you can make in this particular table. Minus 2 volt VBC is minus 2 volt, and the current is dropped to 0. Now what we have to do, we have to stop at this particular point, and then first I will be changing this potential now. Okay, I will be changing, I will be making it 4 volt. So first you make it 4 volt and then continue your experiment. Okay, so how to change this potential? Now at 2 volt again we have to make the reading. Okay, so now if you execute the circuit again, you will be getting certain values. You can see this current 13.238 microamperes. So this is our values. Okay, minus 2 volt we have applied in the input, and then this current is 13.238 microampere. Similarly, this base to collector drop is minus 3.324. Minus 3.324. Okay, here you can see it is minus 3.324. So just try to verify all this table. Okay, again at minus 4 volt it will drop to 0, and then again you have to change the VEC to minus 6 volt. So this way you can obtain the complete data. Fine. So here you can observe one thing when I was explaining you this characteristics. Here you can see this data onto the x-axis is collector to base voltage. Okay, or base to collector voltage. If you write base to collector voltage, it will be a negative values. So it is collector to base drop. So basically here you can see again. Here we are changing the base to collector voltages. These are the values. Okay, it is a minus 1.324, minus 1.3. It is increasing slowly. Okay, in the negative direction, right? With the negative polarity, it is increasing slowly. Again, it is increasing slowly. Minus 2, minus 2.5, minus 3, minus 3.2, minus 3.4, and so on. And then we have obtained this curve for corresponding VEC different values. Okay, corresponding to different VEC values. Okay, so to get this particular curve, what we have to do is, first what we have to do, I have just copied this data. You can see BBC and IV. VBC and IB. Okay, you just copy this data from here to here. Okay, you copy this data. So up to -2 volt, I have already copied. Here you can see this is -2 volt, and this data is corresponding to this is 0. Okay, and then again you have to copy this data. Okay, again at the bottom of this data you have to copy this data again. Okay, then again you copy this data. Okay, and this way I have copied all this data which is obtained for different values of emitter to collector drop. And then you have to go for the plotting. So what you do, just simply select these two data. Okay, and then you can go to the insert, and then here you can find this particular curve. Okay, so this way you can plot this scattered plot. Okay, and here you can see that this plot is actually, this is our negative axis. Okay, and if you wish, you can just plot this, just you reverse the scale. Okay, so if you reverse the scale, you will be able to get this type of curve. Okay, you can just reverse the scale. Fine. If you reverse the values, okay, you will be able to see this particular curve. Fine. So this graph you can obtain. Okay, this graph you can obtain. Fine. So this way you can try to obtain this graph. So here you can see this. This is the curve. Okay, which is corresponding to this input characteristics. Okay, you can just join them. I have just taken the scattered plot. You can take the solid plot, so you will be able to join this curve. Okay, so a beautiful curve like this you will be able to get. This values you can note down. Okay, so this curve is corresponding to V is equals to -2 volt. This is V is equals to -4 volt, and this is V is equals to -6 volt. So this way you will be able to get the input characteristics. And now to obtain the output characteristics. Okay, here I have obtained the output characteristics. Okay, you must be remember in the output characteristics, what we have to perform is, first of all, we have to make this observation table. You remember? Okay, we have to obtain the VI characteristics for this different values of base current. Okay, first we have to make IB equals to 0 ampere microampere, then IB equals to some 10 microamperes. Okay, and then IB equals to 20 microamperes, and so on. Okay, you have to adjust these values. Okay, so I was not able to adjust properly 10 microamperes, so I kept this value as 10.313 microamperes. Okay, so this way we can obtain the characteristics. So you please try to see, we have to vary this voltage. We have to now vary this emitter to collector voltage, and then we have to measure this particular emitter current. Okay, this current we have to measure. Okay, for different for a constant value of base current. Okay, so first we have to set the base current to a particular value. So I'm just showing you a few of the readings. Okay, that will give you certain ideas, and then you will be able to perform the entire experiment. Okay, I'll be just taking this one. Okay, I'm making this IB equals to 10.313 microampere. First I have to set this particular value, IB equals to 10.313 microamperes. So to make this IB equals to 10.313 microamperes, first V in I have to set equals to -1.6 volt. Okay, I'll be making it -1.6 volt. Okay, so I'm just making this value equals to -1.6 volt. Okay, this value is -1.6. Okay, stop it. So first stop it, -1.6 now, and then you can see this values. Okay, I have to keep this VC equals to 0 volt, and then we can observe this values. Okay, so if you make it 0 volt, okay, you just make it 0 volt. Fine. Now if you execute this circuit, okay, try to first execute the circuit and try to observe this current. Okay, this current is 10.223 microampere. This 0 volt, and here it is 10.223 microamps. So this current is 10.223. So either it is 313 or 223. It is a small value. It is near about 10 microamperes. Okay, I have written 2.13. It may be something wrong written here. Okay, so you can just observe this current 10.223 microamperes. So now onwards, what we have to do is we have to keep this current near about 10.223. A small fluctuation may be means tolerable, but you try to keep it around 10.2 to 3 microamperes. If in the laboratory, you may be able to set this particular voltage such that this value will be exactly controlled to 10 microamperes. Okay, but the idea is that we have to keep this base current to be constant. Okay, so once you will making it minus 1.6, this emitter to collector voltage, we have make it 0 volt. Here you can see this corresponding this emitter current. Okay, this emitter current here you can see it is 18.432 microamperes. Okay, so 18.43 microamperes will be corresponding to 0.018 milliamperes. So you can see this value, it is 0.0184 milliamperes. Okay, so this value you are getting as 0.0184 milliamperes. Fine. So again, you can change this V input. Once you will be changing the VCE. Okay, you remember one point which is very important point over here while obtaining the output characteristics, because when we changing the VCE, this IB will not be constant. You remember this point. Okay, this IB will not constant. So try to observe this. Okay, if you make it VC equals to 0.5. Okay, so what I'm doing is you just stop it, and it was 10.223 microampere over here. You can see if you make it 0.5. Okay, if you make it 0.5 volt. Okay, and now if you execute this circuit, you can observe this base current. Okay, this base current will change. It is 14.217 microamperes. Okay, and you must be aware that the base current will be changing because of the base width modulation. Those who have studied the BGT, they must have understood what is the base width modulation. So due to the base width modulation, this base current will change. Okay, so again we have to bring back this base current to its initial value. Okay, means 10.213 whatever it was. Okay, so that value we have to again bring back. So to bring back that particular value, we have to change this V input. Okay, so that this current should be a constant, and then the graph will be obtained for a constant base current. Fine. So what we will be doing, I have already written this value. If you make it minus 1.2 volt, again this current will come back to some around 10 microamperes. Okay, so here you can see if you make it minus 1.2 volt, if you make it minus 1.2 volt. Okay, remember that you have to change the polarity. Okay, this minus 1.2 or minus 1.6, whatever I'm writing, while doing the experiment in the laboratory, you have to change the polarity of the battery. Okay, you cannot put any negative sign. Now, if you execute the circuit, you can see this value is 10.313 microamperes. Okay, so it is near about 10 microamperes. Now the current is equal to its original current. A little bit fluctuation is there, but okay, it will be tolerable and we can conduct our experiment. So now the input current is fixed. Okay, so now we can measure this current. This is our emitter current. Okay, this is our emitter current. So this emitter current is 2.958 milliamperes. Here you can see this current is 2.958 milliamperes. Okay, so this is our current. Similarly, again, if you change this collector to emitter voltage to 1 volt, if you make it 1 volt, you will again observe that this base current will not constant. Again, it will fluctuate. Okay, so if you make it 1 volt, okay, and if you execute the circuit, okay, here you can see that this base current has changed to 15.197 microampere because of the base width modulation. And what we have to do, we have to again change this V input. Okay, so that this current can be brought back to 10 microamperes. So here you can see this value. Okay, if you make it minus 0.7, okay, minus 0.7, then again your current will be coming back to 10 microamperes. Okay, so just make it 0.7, 0.7, okay, this way, and then if you execute it, you will find that this current is again coming back to 10.313 microamperes. Okay, so now again the current is equal to its initial current. Okay, now the corresponding emitter current you can measure here, it is 2.977 milliamperes. Okay, so this current is 2.977 milliamperes. So this way you please try to keep changing this collector to voltage drop. Initially, the step size for the collector to emitter voltage drop I have taken is 0.5. So 0.5, 1 volt, and then 2.5 volt, then 5 volt, 7.5, 10, 12.5, and 15. Okay, so this step size will be sufficient to obtain the VI characteristic. So this way we have to change the collector to emitter voltage. Then again, we have to control this V in. Okay, we have to control this V in. Otherwise, we won't be able to uh, keep this constant current. Okay, this base current cannot be constant. So we have to control this V in. Okay, so that's why I have written over here this V in should be there. Okay, so you have to control this V in. Accordingly, once you have obtained the curve for V, IB equals to 10 microamperes, we have to set IB equals to 20 microamperes. Okay, we have to obtain the curve for IB equals to 0 microamperes. So all this values I have already conducted, all this experiment I have conducted, and then I have noted down this all values. So let's suppose if you make it IB equals to 20 microamperes. So how to obtain this one? Okay, IB equals to 20 microamperes. So what values we have to set? You see, VC should be 0 volt. Okay, so just make it 0 volt. Okay, you just stop it and make it 0 volt. It 0 volt. Then again to make it this IB, if you want to make it 20 microvolt, here you can see the corresponding V in value. Okay, this V in minus 2.6 volt will make this IB current equals to 20 micro ampere. Okay, so make it minus 2.6, right? So just make it minus 2.6 and try to, you will be able to observe this value. So this is 20 microampere. Okay. So this way you have to control your base current. You remember that for a constant base current, you have to obtain this common collector output characteristics. Okay. By varying this VEC and measuring the emitter current. Fine. So this current is 41.941 microamperes. So that you can written over here. This current is 0.012 milliamperes, 0.042. Okay. So here you can see it is in the microamps. So that value you can write in the milliamperes as 0.042 milliamperes. So hopefully how to perform this experiment must be clear. Okay. So just you try to obtain this table, this observation table. Okay. Try to observe this complete table. The same thing you can also perform onto the breadboard. A similar experiment you have to perform. The procedure will be remain same. And then you have to obtain this family of curve for IB equals to 0 microamperes, IB equals to 10 microamperes, 20, 30, 40, 50, and so on. Okay. You have to fill this complete table. You have to keep in mind about the step size of the collector to emitter voltage. Okay. Because I written there, it is emitter to collector voltage. This voltage is negative. So if you write collector to emitter voltage, it will become positive. Okay. So this way you have to obtain your characteristics. Okay. To draw this particular graph. Okay. This graph is having onto the x-axis, we are having the collector to emitter voltage drop, and onto this axis, we are having this particular emitter current. Okay. So to obtain this curve, just you select this particular column, and then you select all the corresponding IE columns. Okay. This column, then again, you have to select this column corresponding to IB equals to 10 microamperes, then this column, then this column, and then again this column. So while selecting, I have just pressed the control button onto the keyboard, and then you can select each of them. Okay. And then again, you can go to the insert tab. Here you can find this, and then you can plot the corresponding curve. Okay. So whatever curve you can obtain. Okay. This way you can plot your curve. A similar curve we are going to get. Okay. So hopefully you must be able to obtain the VI characteristics. So try to obtain the this input and output characteristics. You remember that the input characteristics of common collector configuration is very peculiar. Okay. You won't find such characteristics in any other configuration. So, okay, if you see your common base configuration or common emitter configuration, their input characteristics are similar. Okay. But here you can find that in the common collector, the input characteristics is quite different. Okay. It is quite different. It is very different from the other input characteristics. So I hope you must have learned something from this video. So please stay connected with the channel. And if you find any difficulty, you can write your doubts by posting your comments. Okay. So thank you for watching this video. Stay connected with the channel. Thank you.